record here. Cosine graph over the interval of 0 to 2 pi. Although I'm not going to need all of that, I'm including all of it. All right, because when we look at a trig wave, we want to usually look for one full cycle of the trig wave. All right, so typically that's 0 to 2 pi. All right, for the parent function anyway. So let us get some points here. This one would be what? That first point that I plotted? 0, 1. Get an x-intercept here. What's my x-intercept? My first one anyway. Something comma 0. What's the something? Pi over 2. All right. The minimum point? Pi negative 1. And then we can keep going from there, but let's just stop at this point. All right. Because if I'm taking, or if I'm looking for the inverse, I'm really looking at the reflection over the line y equals x of any point xy, the result of which is some point yx. All right, so that was your license behind switching x with y in a function and then solving for y in order to come up with an inverse function. All right, so how would we do that algebraically if I'm dealing with just a cosine wave? Same idea. So I'd have y equals the cosine of x, switch the x with the y, but then we'd have to solve for y. So the question would be, all right, well, how do I get y alone? I can't just divide by COS. It's not a thing because it's cosine of y, not cosine times y. Somehow I have to break up that right-hand side. And the way to do it would be to take the inverse of the right-hand side and then the inverse of the left-hand side. All right, a pre-calc rule. That's, you know, we come back to it a few times, but it's not like a daily occurrence. That's the composition of a function and its inverse. Always give a result of whatever the argument is within the function, right? So x. All right, so composition of a function and its inverse, the reverse is true. So the inverse function on the outside with the original function on the inside would also have the same relationship. Bottom line is the right-hand side becomes just a y. All right, so I have inverse cosine of x equal to y. That's going to be an important detail down the line because here we're working with points, here we're working with equations. You know when we take derivatives, we're working with entire functions, all right? So not just coordinates. We find the derivative and then we work with the individual coordinates, all right? So that's a little bit of the Algebra 2 pre-calc behind it. This step, going from here to here, and actually, I don't know, maybe even the whole process, it may not have been something that you really did a lot with because it could have been just, listen, y equals cosine of x is your original function, so y equals the inverse cosine of x would be the inverse function. Why? Because it's got inverse in its name. You need more explanation than that? Wait till next year. You know, like it could have been something along those lines. It all depends on, you know, the structure of whatever course you're in. So anyway, to come up with a graph, well, on the calculator, we had y equals the inverse cosine of x. Going by points on a calculator with trig functions can be a little iffy. So we'll go with the coordinates on our little makeshift graph here. All right, so what I'm doing is I'm swapping x with y for each of my relevant points. All right, we'll start with these three. I'm looking at 0, 1 becoming 1, 0. So I'll plot that. Pi over 2 comma 0 becomes 0 comma pi over 2. I'll make that pi over 2. Not tau, pi. All right. And then pi comma negative 1 would become negative 1 comma pi. All right. So we have a little bit of a scale here. Here's negative 1. Pi would be somewhere up here. So we're talking about a point like this. All right. So that would be a graph consistent with the arc cosine function. All right. Now, you might say, well, how do we know to stop at pi? What if I wanted to go to 3 pi over 2? Well, if you think about what would happen if I plotted 3 pi over 2 comma 0 as a reverse, it would become 0 comma 3 pi over 2, puts me back on the y-axis. What happens to my inverse graph? It's not a function. It would fail the vertical line test. All right. So what we would want are only points in the original function that pass the horizontal line test. Those would be the points that we use in making our inverse function. So then the question would be, it's a natural question, well, why these points? Why not other points? You know, maybe I wanted to go the other way. You know, I could have created a graph that had some negative domain. And that would be perfectly fine. You know, instead of going, instead of going from 0 to pi, maybe I go from negative pi to 0. Right? Maybe I go from pi to 2 pi. All possibilities. But if you're looking for the most convenient interval, I think we have it, 0 to pi. Anything beyond that, well, this interval, pi to 2 pi, would not include 0. And 0 is the best number ever because it's 0, and it makes life so much easier under almost all circumstances. Right? And over here, even though it incorporates 0, it's got negative values, whereas over here we only have positive values. So just out of convenience, we live in the world of 0 to pi. Now, that addresses that domain. Now, when you're getting into something like the arc secant would follow whatever domain the arc cosine function follows. All right, and that's because the arc secant graph is based off of your arc cosine graph. All right, so you know you could actually just do a quick sketch if you know what a cosine graph looks like. I'm not going to do it on the big screen because it's really not necessary. But if you know what your cosine graph looks like, then anywhere you have an x-intercept for cosine, you're going to have a vertical asymptote for secant. And all you would be doing is taking the reciprocal of whatever the graph is. So here I'd be looking at, instead of going downward, I'd be going upward. Here I have a curve that's going in the upward direction, I'd have it going in the downward direction, approaching the vertical asymptote, and so on. All right. The moral of the story here is, for almost all points where cosine exists, the secant function, the arc secant function, would exist also. So that's the original cosine graph. It would correspond to an inverse graph, but it would have the same characteristics in terms of domain and range, except for the fact that it can't be equal to pi over 2 because that's where the vertical asymptote is. All right. So that's the justification behind the other relationships. All right. It all kind of goes hand in hand. All right. The cotangent will be addressed a little bit more when we talk about what the tangent graph looks like. Let me get a sip of water. All right, but let's look at the sine graph first. All right, so sine graph starts at 0, 0. then it goes to its maximum point, then back down, and so I mean, you could draw as much or as little of the sine graph as you want, but really a lot of it's going to end up being irrelevant, because once you get to a point in the curve where it would fail the horizontal line test, you would stop drawing the graph. So I would actually stop this guy right here, right, making all of this irrelevant. All right, but I want to make sure that I'm accounting for all possible elements in the domain and range of the sine graph that would actually transfer to the arcsine graph. All right, so this is telling me that I would need to work backwards and create part of the sine wave going in the negative direction. Do the same thing. After a certain period, you realize that I don't need any more of the sine graph. I'd stop here because, again, if I go further, if I loop back around, it fails the horizontal line test, and I know that my inverse graph would fail the vertical line test. All right. So it's telling me to live from here to here, which would account for all values in the range, because this is going from negative pi over 2, comma, negative 1, all the way up to pi over 2, comma, positive 1, including the 0, 0 in the middle. All right, so that would be the relevant piece. So I want that to end up helping me generate my inverse sine graph. So plot those points backwards. I don't think we need to do it with the equation directly because it's going to work out the same way as the cosine. I did red. Oh, I'll keep it with red. So negative 1 comma negative pi over 2. Put that right there. Put a 1 here, put a pi over 2 here. We got a 0, 0, and then we would have a 1 comma pi over 2. So you're looking at something like this. Don't go too crazy. Let me thicken it up. I want it to look like nice, like. All right, I mean, it's not terrible. Yeah, sure. All right. So that's what our sine graph would look like, or our arcsine graph. That only exists, the relevant piece for the arcsine only exists between negative pi over 2 and pi over 2. Now let's take a look very quickly at a little ASTC action here. In terms of the quadrants for the arc cosine, we're talking first quadrant. It's not a quality check mark. And in fact, this is now too thick. Not happy with it. Do it like this. Undo. In order to draw a straight line, I actually have to hit the line draw tool every single time. That's infuriating. We eventually get to a point where I can have a mental uplink, and I can just think what I want it to display, and we'll do it. Yeah, so this is from 0 to pi. So 0 to pi is first quadrant, second quadrant. So here and here. The arc sine is going from negative pi over 2 to pi over 2, so that's fourth quadrant, first quadrant. Right? So what we want is now an arctangent graph, because I have the domain there, but to see how that corresponds with an arcsine graph, it's not the easiest thing in the world to see. But then again, if we can see what's going on with arctangent, then we'll see what's going on with arccotangent. Right. So there's really no way on Earth you have enough room for this, right? So separate paper, I guess. I have infinite, because Infinite, yeah. That's what they call it. It's like infinite whiteboard, I think. Oh, the shape is matched, yay. That's what it says. So this is going to be y equals a tangent of x. I'm only going to draw one cycle because we know on the interval of negative pi over 2 to pi over 2, we have some continuous tangent graph, but there are those asymptotes at every multiple of pi over 2. All right. So I could draw my curve. It goes through the origin. And it looks something like that. All right. And to be honest with you, this is really enough to justify the statement about the arctangent, how it's between negative pi over 2 and pi over 2. Just because if you think about it, everything's changed, right? Between domain and range, x and y, whatever you have in your original universe, in the alternate reality, everything gets reversed, right? So when you're finding the inverse function, domain becomes range, range becomes domain, right? Since all of those relations, those inequalities are addressing the range, if I can just identify the domain, the relevant domain for my original function, then I know the range of its inverse, right? But in terms of the graph, the shape is probably more than adequate to get us the idea. We don't necessarily need to do it point by point, although you're welcome to, because it's really, I mean, if you have a good sense of the unit circle, it's not challenging. Tan of x. Here's pi over 4. What is the y value at pi over 4? 1, exactly. All right. So if I were creating by points the arctangent graph, I would plot, instead of pi over 4 comma 1, I would plot 1 comma pi over 4. All right. But again, since everything's changing from one universe or one reality to another, it really is just a matter of saying, okay, what is x will now become y. What is y will now become x. So I have a vertical asymptote at negative pi over 2, so now I'll have a horizontal asymptote at negative pi over 2. Same thing for positive pi over 2. All right, 0, 0 is going to remain 0, 0. This would be pi over 4, negative pi over 4. I'd have to establish a little bit of a scale for 1 and negative 1, but I could put those wherever I want. Here's 1, here's negative 1. Call this pi over 4. Plot some points. Make it blue. So you'd be looking at something like this. And again, since all of those inequalities are addressing the range of the inverse trig function, it's pretty clear here that it's going to be going to negative pi over 2 on the low end, positive pi over 2 on the high end for the range of arctangent. All right. Now, the arctangent function, that would be like, all right, you got to do a whole new graph for that? Well, no, because the arctangent is based off of the graph of the just cotangent function. And the cotangent function has the same structure as the tangent graph, except it's going downhill from left to right. I mean, the asymptotes don't line up perfectly, but it still has the same general structure. So a rough sketch would be all you would need. You'd have something with a pair of asymptotes and then a downhill relationship. So your arctangent
would have a couple of horizontal asymptotes and also a downward facing structure. So something along those lines. All right, so I don't need point by point in order to get it for me. I just needed to have a sense of it. As long as I know where the asymptotes are, I'm good. For cotangent, the denominator, if I put it in sine cosine form, the denominator is sine. Where is the sine function equal to 0? 0 and pi, among others, but those are the two that we would care about if we were creating asymptotes. All right, so if you're looking back at the ranges that were given here for the arc cosine, you'd have arc cotangent going from 0 to pi because they're consistent with wherever sine is equal to 0. All right, whereas arctangent is consistent with wherever cosine is equal to 0. All right, so strange but useful stuff. I don't know if people are still getting this down, so I'll just leave it there for a sec. So bearing in mind that we can only, if we're dealing with the arc sine, we can only be in the interval, highlighter, yellow, this interval here, negative pi over 2 to pi over 2, I'd be looking for the value in the unit circle that has, so the angle in the unit circle that has a ratio of negative 1/2. The result of an arc function is always an angle. Result is some angle theta. All right, so you're thinking about your unit circle. You're thinking about all the ratios that exist within the unit circle. Sine is the set of y values around that unit circle. Only in the appropriate areas. So in this case, fourth quadrant, first quadrant, what angle has a y value of negative 1/2? What, say it again? I think I heard it. Close. Negative pi over 6. All right. Sine of pi over 6. You know, you could check it by taking the sine of whatever the angle is. Sine of pi over 6 would be the positive 1/2 because that's first quadrant. Negative pi over 6 puts it in the fourth quadrant. By ASTC, only cosine's positive, you know, and it's reciprocal. So it would naturally give us a negative result. All right. Inverse cosine. Again, the result of an inverse function should be some angle. So this result should be some angle theta. We have a ratio. Because it's inverse cosine, we're only living in the first or second quadrants. It's a negative ratio, so definitely not in the first quadrant. Cosine within a coordinate on our unit circle, cosine is the x value. So what theta has an x value in the second quadrant of negative radical 2 over 2? Three pi over 4. All right, domain is, yeah, so negative 5 pi over 4 would be a coterminal angle. It's getting to the same location, but since it's not within the domain, it's not technically possible. So if it's not possible, it can't be an answer. All right. These problems, well, instead use your calculator, so we'll use our calculator. But, you know, there's often more to it than that. So arctan, so I'll just do arctan, negative 0.3. No problem whatsoever. Making sure I'm in the right mode, radian mode. Nice and easy. You're like, so 3 examples for something that's nice and easy, huh? Oh yeah. We like to spend some time with nice and easy where we can. All right, we got a decimal value. It's some multiple of pi. It's a radian measure. It's some multiple of pi, hence the nastiness of the decimal. But that doesn't mean you could write it as a multiple of pi. You could try. Divide out the pi, math bracket. It's not going to work. And that's because the ratio that you're given is not a unit circle ratio. So we're not expecting nice answers. Right? Sometimes you could end up, you could have a ratio that's not a unit circle ratio, you could get something like, I don't know, pi over 21 in there. I'm sorry, not pi over 21, like radical 21 over 7, something along those lines. And it gives you something that can be math fracked out, but that's very rare. You're not expecting that. You get to something like b, and you see it's arc cosecant. So you start thinking about, well, how could I even think about doing that? Well, arc cosecant is 1 over the arc sine, 1 over the arc sine. But then you plug in the negative 2.4, and I don't even hit enter because the inverse sine function is related to ratios for the sine function. Sine only exists between negative 1 and 1. So the minute I put a value in for the inverse sine function that's more than 1 or less than negative 1, I'm going to get an error message. Right? The issue here is arc cosecant, kind of along the same lines as arc secant. It doesn't have the same restrictions as sine, right? Where sine has to be between negative 1 and 1, arc sine, cosecant would be anywhere but the interval between negative 1 and 1. So negative 2.4 is perfectly fine for an arc cosecant, just not for an arc sine. So how do we handle it? Well, if I know the result is going to be some value theta, I could take the cosecant of both sides. I'm going to write it out. So it's the cosecant of the arc cosecant of negative 2.4. Left-hand side, it would just be a negative 2.4 by the laws of pre-calc. You don't necessarily have to show this work. I just like to show it because I don't think you get enough of it on the lower levels. You know, like just jump right to it. Just put it in your calculator, get an answer, look at the graph, you know, things like that without really understanding why you're doing it. Not always the case, but I can't assume that it is the case, so we go from there. Anyway, you can, at this point, do a lot of things. One thing would be to convert over from cosecant to something more familiar like sine. 1 over the sine of theta would be equal to negative 2.4. I can write this as the sine of theta is equal to 1 over negative 2.4 or negative 1 over 2.4, either way. This is something you could work in your calculator. Okay? We would take the arc sine of both sides. Again, I'm showing more detail than I need to because I want to come up with a general approach. All right, so I'd be taking the arc sine of both sides. So on the left, it would become theta equals. On the right, it would become the inverse sine of 1 over negative 2.4, again, or negative 1 over positive 2.4. All right. Perfectly fine to put that in your calculator now. You'll get the answer, but it also shows us a way in which we could have gotten that without doing any work. So you get about negative 0.43-ish. So theta is negative 0.43 radians, approximately. But get something a little nicer out of this. All right? Because again, the calculator doesn't have arc cosecant buttons or arc secant or arc cotangent. It has arc sine, arc cosine, arc tangent, and that's it. Right? So what this tells me is that I can put this directly in my calculator as long as I take the reciprocal of all parts. All right? So I'm taking the reciprocal of the cosecant to make it sine, but I'd also have to take the reciprocal of the ratio. All right, so the justification of that is algebraic, yes. However, it's also graphical, because if I'm looking at this as a ratio, for example, of cotangent, the ratio, well, tangent is opposite over adjacent, so this would be adjacent over opposite. I could draw a right triangle with an angle theta, an unknown angle theta, that has this ratio. The adjacent side being 3, with the opposite side being what? 1. All right. I could figure out the missing side if I wanted to using the Pythagorean theorem. And then I have the choice of any possible ratio I want. But based on what I have here, I might say, okay, well, from this triangle, I see a tangent ratio, tangent of theta, is opposite over adjacent, which would be 1/3. So that's telling me that the inverse cotangent of 3 would be the same as the inverse tangent of 1/3. All right, so take the reciprocal of both parts. Geometrically, it plays out nicely. You get 0.322 roughly. In the past, what I would do, and it really didn't matter what level of calculus it was, AP, college, non-AP, it didn't make a difference. I would jump right to the algebraic stuff, working with x's and finding derivatives and things like that. And almost universally, people would be like, I don't know how or why on earth you're able to do any of the stuff that you're telling us that we're able to do. And my thinking brought everyone back to pre-calc and the idea that it was either not covered, or it was covered briefly, or it was covered in depth, but in like October of the previous year. So it was generally one of those 3 things. Bottom line is it required a little bit of review, and by a little I meant a lot. Right. So did any of this look familiar? Yeah, right? Did these concepts here, is that something you knew?
The third one.
The third one?
Jumped right to kind of the second, like in B, we just would have done.
Like here's the rule, go for it, yeah. All right, so hopefully it adds a little bit of context. I don't think, or at least I hope it wasn't a waste of time. That's the idea anyway. All right, so if that gives you a little bit more of an idea about how to tackle that sheet, that's a good thing. We can talk about that more tomorrow, then we'll get into the calculus of it.